Okay, so now we'll try to understand what will be the heat transfer conditions when the fluid actually flowing over a cylinder or a sphere. This is very important, and we will get um, a lot of charts and the tables for this sections. This is all of you know. Let's say this is a cylinder, and the flow is when flow is just coming this way, we can see that some flow separations happen, and later on some mixing. So the flow mix together. So the flow separation it is difficult to handle analytically. So we need some benchmark experiment or we need some numerical steps or solutions to analyze this. So for cylinder or sphere, whatever it is, the flow separations and the flow mixing is a complex phenomenon, and we actually need to solve some problem in real life. Okay, so we need to calculate the heat transfer associated with this phenomenon. So what actually happened um, when but the complicated this flow um, across a sphere or cylinder, it actually influenced the heat transfer. So depending on the local Nusselt number or the convection heat transfer coefficient, actually you can see this chart here. This x-axis is showing the stagnation point or the angle, and this is showing the Nusselt numbers. So we can see like with this stagnation angle, you can see the angle definition from here. You do not need to understand this one a lot, but just some visualization. You see, when this angle increasing, it's decreased like this. At this point, you see, this is the point. It becomes kind of, you see, the 80 degree. So here for this both cases, this stagnation angle it becomes 80 degree. Actually, when the angle increase, when the initially the angle is zero, you see the value, it is this number value is higher. When it increase, okay, the you mean this is the angle theta. What happened? The laminar boundary layer it becomes thickened, and that means actually this Nusselt number it decreases. The Nusselt number will decrease, and at this point it becomes 80 degree kind of. It is the flow separation point in laminar flow. And then when the intense mixing happens, then it starts increasing again. You see for some cases some increasing trend. So we'll discuss it. We'll actually discuss and we'll show some visualizations later on. The intention is how we can calculate the Nusselt number, the heat transfer coefficient, or total rate of heat transfer for the flow over cylinders and spheres. So here, when for a flow over a cylinder, this is actually the Nusselt number correlations. So we will use this Nusselt number correlations for this types of problem when it is a cylinder, but for a sphere, we will use this. Just keep in mind, in that case, we'll use the film temperature. Film temperature is this is the cylinder, so the flow is going this way. So this is actually what is happening. We'll say Ts, this is the surface temperature, and T infinity is the air temperature. So just the half of this, it is called the film temperature. So for flow over a sphere, we'll use this. Okay. So this is the case. So we'll use these two formulas actually for any types of problem related to the cylinder and sphere. But for the average Nusselt number, we can use these expressions for more accuracy. Here, this is more the easy the simple expressions, but we have a couple of constant the c's and the m and the n. So how we can get it? We can get it from this. Here is actually all expressions for different types of geometry for circle, square, and the tilted square, and for different fluids, for different Reynolds number, here is the corresponding expression. So if when the flow is passing just over this cylinder or this kinds of irregular shape, square, tilted square, then here is the corresponding expression. So you will get it in the question in the exam, maybe the flow passing a square or a tilted square, and we will ask you, okay, calculate the heat transfer coefficient. So let's say the first task will be you need to calculate the Reynolds number, and if you see the Reynolds number is in between this value, then you will use this Nusselt number expressions. So once you have this Nusselt number, then from the Nusselt number, you will get the heat transfer coefficient or the total rate of heat transfer. So we will show you how to do that. It is very easy problem. So all the questions, it's kind of similar pattern for these heat transfer sections. Here, some other geometries like the hexagon, the vertical plate, the ellipse. You see all the related expressions here. So you do not need to, actually develop or drive any theories in this case. But what you need to know is, for general problem, you can use this for cylinder, for sphere this, or for any other shape geometry, then we will be using all these tables. So everything is given here. So based on the given informations, and when the flow, we'll calculate the Reynolds number, and then we'll decide which correlations we should use here. So we'll solve related problems during the tutorials and the lectures, and you will get much better understanding. So that's all.